show you an example of how to use what we've learned so far into making a 3D dynamic simulation and then animation. Okay, so 3D dynamics. So what we'll do is we'll choose a regular shaped body, a cuboid. And so it is, let's say like this. And sorry, X, this should be C. This is Y. Okay, and then it's under gravity. And so the question is given an initial speed. So it'll be Vx, Vy, Vz. It could be in the angular speed, could be in body frame or fixed frame, or it could be Euler rates. Let me just use Euler rates. Say so phi dot, theta dot, psi dot, and of course the positions. Phi thetas. So the initial given initial speed and position, describe the motion of the object. So this involves basically deriving the equations. Second step is to simulate the system. Now that's actually very simple. It's just ODE45, just simulate and animate the system. So animate is something which I'm going to reuse the code I've used before for this object. So that's so simple. The harder part is probably the derivation of the equations, right? Everything else you've done so many times in this course. So let's see how to do that. So let's do deriving equations. Okay, so what we do, we use Euler Lagrange equations or Euler Lagrange method. The first step is to find the positions of so position of center of mass. Okay, so the positions is, well, the x, y, z position is simply x, y, z, and then for the rotations we'll use Euler 3-to-1 angle. So 3-to-1 Euler. So in this case it'll be psi about z, theta about y, and phi about x. So that's fine. So that was easy. Then we need to find the velocity. And the velocity is simply x dot, y dot, z dot, or if you like to call it vx, vy, vz. Okay. And then comes angular velocity. So this is where things are slightly different from 2D case. Now, what you will see is that, well, we have the Euler rates, we have the angular velocity in body frame, we have angular velocity in the fixed frame. Okay, so Euler rates by themselves are nothing but they don't really give us angular speed, right? Directly, we need to find a relation between them and the angular speed. But we are stuck with the Euler rates because we use the Euler angles to represent the rotation. So those derivatives will be available to us. So we need to write angular velocity. And as you'll see is that it's best to actually use the angular velocity in the body frame. Why I do that will be clear in just a minute. So if the angular velocity in body frame is omega x, omega y, omega z, then we derived a formula which relates these angular speeds with the Euler rates. So phi dot theta dot and psi dot. So that is 1, 0, 0, 0 cosine phi minus sine phi, and then minus sine theta cos theta sine phi, and then cos theta cos phi. Okay, so given these angles, the Euler angles, and given the rates phi dot, theta dot, psi dot, and those are actually initialized. Those are going to be given to us at the start. We can actually find the angular speed. So that's not a problem. So this is what we did in just a few minutes back. Now let's get to the next part, which is finding the total energy. Now the total energy is given by the Lagrangian is given by T minus B, where B is actually pretty simple. It's mass times gravity times the height. In this case, gravity acts along the z direction, so it's just mgz. Now, the kinetic energy is given by 0.5 mass times x dot square plus y dot square plus z dot square. Okay, and now comes the part where we need to write the angular speed in. Well, we need to find the rotational energy, and the formula for rotational energy is omega transpose I omega. This, by the way, can also be written as mass times V transpose times V, where V is x dot, y dot, z dot. But when you take the multiplication, it basically boils down to x dot square plus y dot square. So this is, I'm using the angular speed in fixed frame. So this should be fixed, right? Okay, what does this mean? Well, it says that if there's a body like this and x, y, and z. So in this configuration is a nice configuration because the angular speed omega and angular speed in the body frame and the fixed frame is the same, because the fixed frame and the body frame are along the same axis, right? Now, when you rotate the body, let's say that this is my original x, y, z, and let's say that it's rotated, it's something like this. And this is, by the way, this is the body frame. So x prime, y prime, sort of clutter. Let me change the color. I'm just going to randomly draw something like this. It's some orientation with the fixed xyz. Okay, now this is x prime, and then let's say this is y prime, and then z prime. Okay, so x prime, y prime, z prime as is body frame. Prime says body, and other one is the fixed frame. Now, what you will see is that when this object is rotating, the inertia about the fixed frame is actually changing. So what is the inertia about the x-axis? Well, in this case, you know the inertia. It's basically a formula from the table. Now I ask you, what is the inertia about x? That inertia is not the same as the inertia about this x, because the object has actually rotated. So it's just so hard to keep the track of the inertia in the fixed frame. Okay, and so if we need to plug in the value for inertia by computing the inertia in about this axis xyz when it is rotated is hard, and then you know this formula, but then getting that I fixed is really hard. So this is complex. So we don't do this. We actually will not use this formula. We'll actually use the inertia in the body frame. So it'll be omega transpose I omega. So this is in the body frame. The good thing about the body frame is that that's going to be inertia about x in this case, which is the same as fixed frame. But now it's the inertia about this x prime, y prime, z prime. And x prime, y prime is the body frame. So it's the inertia in frame x prime, y prime, z prime is the same as the inertia about x, y, z. And so no matter how the object rotates, that inertia is going to be fixed. So it doesn't change. And it's already usually available in tables. If you look textbooks, they'll give you inertia about the principal axis. So that's the inertia you use. Or it is available in the files, in the, what do you call, the CAD files. They will give you the principal inertia. So you're better off using the body frame inertia because it does not change basically as the orientation change. It does not change with orientation changes. Okay, now here's the thing. This energy is the same as this energy. Okay, there's no difference between the two. So no matter how you choose the energy, body or fixed frame, the energy won't change. Just that computation will be different from the other. So what we do is, so to summarize, what we do is we write the energy as follows. T equals 0.5 m x dot square plus y dot square plus z dot square plus 0.5 capital omega transpose I body frame omega. Okay, where this omega is that same one which I wrote down, omega x, omega y, omega z, which is now a function of phi theta dot, phi dot, and psi dot, and it'll also have phi theta, phi psi, right? It's basically the formula I wrote down earlier. So the interesting thing here to note is that this is in fixed frame. We find the kinetic energy due to translation in the fixed frame. However, we find the energy in the due to rotation about the body frame, which means that you need to find the position in fixed frame, world frame, global frame, and you need to find the angular velocity in body frame so that you can use this formula. So once we have this formula, okay, then we can then use the same trick we use, well, the same formula for Euler Lagrange equations to get the equation. So we have L, which is T minus P. The third and the final step is to derive the equations using d dt dl dq dot minus dl dq equals qj, and this should be j, where now qj will be the following. It will be x, y, z, phi, theta, and psi. So it'll be 6 variables, or 6 DOFs, or degrees of freedom. There'll be 6 equations corresponding to 3 translations, 3 rotations. And then when you get this formula, you'll basically end up getting something like this. AX equals B, where this will be 6, 6, 6, 1, 6, 1. X in this case is the rate of change of Q. So it's Q double dot. Maybe I should just write it as Q double dot, right? Where Q is the degrees of freedom. And once you get that, you can then find Q double dot as A/B in MATLAB to make computation simple. So I'll show you how to implement this in MATLAB and show you animation of the following. But this is the most critical part, is to derive these equations. Here is my code. This code basically derives the equations. So I define all the quantities of interest. In this case, I chose the inertia such that you only have principal axis. So the inertia is described about the principal axis. And so you don't have the x, y, and the y, z, and the x, z components. So then the rotation matrices Rx, Ry, Rz. I find the angular velocity, which is basically this formula I wrote down. I did not simplify it, or like I simplified in my notes, but I just made MATLAB simplify it. The inertia is, as I said, along the principal axis, so only the diagonal components will be non-zero. The velocity in global frame, the total energy, and then this is V transpose times V, and this omega B transpose times I omega, and then the potential energy. Okay, so when I do this, take Q double dot, run this formula for all to get the 6 equations, and then I just go. So if I click that, it will just give me those equations, those A and B, and then I go some extra steps. For example, I find the angular velocity in world frame. I find the angular velocity in body frame, which I'd done it earlier. I don't know why I did it again. And then I wrote down it in a nice compact way so I can use it to find the angular speed. So if you're interested in finding the angular velocity in one or two other frame, you can use this. So then I need to take this part, which is the B's and the A's, copy that. So copy that and go to this code. And this is somewhere there'll be a right-hand side. See the right hand side. So there it is. So I copy pasted this from equations, equations falling block, this file. Okay, everything here. Okay, and then I get the rate of change, the acceleration. So then I basically put it in z dot, which is the rate of change. And then I send that using my equations of motion to the ODE function, which is, I believe here. So ODE 45 EOM is the equation. So I just run this. It basically show a block which starts off with certain parameters, but starts off with zero speed. There's a speed of 5 meters per second in the vertical direction, so against gravity. And then all the initial angular positions are zero, but then I impart some angular speeds in the Euler sense. So Euler rates have been not zero. So let me run this. Okay, and some plots. So I can give this something else, 1.2, 5, 4, 10. So now it's spinning too much about the z-axis because I gave a high psi dot. Okay, so you can basically play with this and get it to do interesting.